slides being available at the end of the presentation. We'll be sending the slides out within 24 hours of the end of the presentation. Okay, so let's go ahead and get started this morning. This is Jeff Mucci again from RCR Wireless News. Today we have Philip Sorrells, John Cole, Tom Anderson from CommScope who will be leading this presentation. Before we get started, I'm going to put up a poll, and we'd like the input from the attendees, and this will give us a better sense for your areas of interest. So you'll see a poll on your screen now. What is the current state of backhaul in your view? We'll leave this open for about 30 seconds for people to submit their responses. And then we'll display the responses at the end of the presentation before we go into Q&A. So again, I'd ask folks to indicate your response to our first poll and remind everyone that questions are welcome throughout the presentation. Well, I'm looking at the results, and I can tell you they're running about neck and neck on the first three opportunities to respond. So we appreciate everybody submitting their response and vote on the poll. We're up to about 60% of the people voting. Wait a few more seconds and see if we can't get 75% of the attendees to cast their poll. Okay, we're going to close the poll now. And Philip, I'll turn it over to you. Philip Sorrells is going to lead the initial part of the presentation. He's VP of Site Solutions for CommScope.
Well, thank you so much. And first off, before I get started, I'd just like to say on behalf of CommScope, thank you to the staff at RCR for hosting us for this webinar. It's always a pleasure to talk with like-minded problems about the challenges of our industry. We can just go to the next slide, slide number 2. There's just no question at all that the wireless market has huge opportunities going forward. No matter where you look, all evidence shows that the demand for wireless voice and data services will continue to grow. Overall, most operators express that capacity is their top concern today, both on the access side and on the backhaul side of the network. But many believe that backhaul capacity is the most urgent challenge and point out that building access capacity too far ahead of backhaul is a poor economic choice. We agree with that. And we are moving forward with approaches, I believe, that can help our customers add capacity. We're going to address both microwave air access and our fiber to the cell initiatives in our presentations today. So let's take a look at the next slide. The ecosystem for backhaul really exists in two primary areas. The most dominant area in the wireless network is really the backhaul that's required for the macro BTS applications, which really connect the conventional BTS to the mobile core or backbone network. This system provides thousands of interleaved phone, email, data call transactions and millions of data packages that stream out from multiple thousands of users. Today, that backhaul ecosystem is served by microwave, fiber, copper, and in some areas, satellite. A growing area for backhaul applications is in the area of small cells. Small cell is the future emerging trend, we believe, in wireless, and backhaul is a critical consideration in that area. Small cell is typically applied for adding capacity overall to the network in femtos and picos and microcell type applications, and a number in users from the tens to 200 user level. The difference here is that we see backhaul in the small cell area also using other technology approaches that include DSL, Wi-Fi, non-line of sight, radio links, unlicensed radio links, as well as fiber and air microwave applications. So if we take a look at the next slide, please. The next slide shows just generally how the technology of the provision of backhaul services is occurring today, and it's projected out through 2015. And as you can see here, the air interface, typically the microwave backhaul link, serves about half the market, a little over half the market today. And we see that continuing to grow in need as applications grow. And then we see that the fiber to the cell type applications also continues to grow, replacing, we believe, much of the copper type applications in the future. With that, I will introduce John Cole. So let's just go to the next slide. John Cole is our Director of Product Management for our Microwave Antenna Division. You may be very aware that CommScope, through our Andrew brand, is the leading provider of microwave antenna systems in the world, and John has some great initiatives that we've introduced to add capacity into the backhaul link. John, I'll turn it to you.
Thanks, Philip. So, hello everyone. I'm speaking to you today from Scotland, where it's raining. I'm going to speak about a handful of breakthrough technologies. I'm going to limit my conversation primarily to microwave point-to-point. The frequency bands conventionally for this technology are perhaps 6 gigahertz through to 42 gigahertz. However, I would like to imply that there are relevant remarks and aspects of this discussion to line of sight millimeter wave technologies that are emerging perhaps for small cell applications. So I feel like there's an implicit small cell content to this presentation, but generally I'm going to focus on line of sight microwave. Next slide, please. So firstly, I'll open the discussion with a negative topic. I won't apologize for that, but it's a disappointment to me that I feel I need to. As we have been a member of the industry for many years, we observed a concern, had a concern with regard to the performance of backhaul networks for microwave applications. And it became apparent to us that we needed to work at the root cause to understand where the issues were primarily centered from. And my slide here is intended to try to emphasize that data loss, of course, a loss of traffic in the transport streams on a microwave link will translate and can and do translate directly into the performance of the network. And quite often when you are frustrated with your handset and you drop that call, I suspect we all imagine that it's something to do with the immediate connection in the immediate vicinity in the RAN network. However, it is the case that calls are being dropped on the transport data link, and problems occur in the transport streams of the various types. So in microwave, the effect of this issue has become more and more prevalent. However, I must say it's a regional issue, predominantly in developing countries, but is a threat to us all. So I'm going to talk to this a little bit more. Next slide, please. So using an advanced software tool to demonstrate or to understand more about our concern, we modeled a network, a backhaul network in Spain that had 10,000 microwave links in it. And the network was designed with known radiation pattern characteristics for the antennas to be utilized. And those antennas conformed and complied in the model with a Class 3 specification, so the standard freely available specification for antennas on the market today. We then imported the actual characteristics of antennas that have been taken down from the networks and measured. So in other words, the actual off-axis radiation results for a group of antennas that are freely available in the industry. We also imported into that software model some Class 2 antenna characteristics. So we felt we put a reasonable spread of true characteristics as opposed to the declared characteristics from the antenna manufacturer. And sadly, we observed that as many as a third of the radio links did not comply with their availability specification. So in other words, packets were being lost in the network. Frankly, the issue is really quite dramatic, but that paper is available to you after this, along with other papers on a similar topic. Next slide, please. So to be more specific, the graph on the left-hand side, top left-hand side there, is a radiation pattern of a microwave antenna. The vertical axis is 0 to 80 dBs. The horizontal axis is 0 plus or minus 180 degrees. So the true azimuthal measurement of energy around that antenna through 360 degrees. And as you would expect, at 0 degrees there's very high energy, normalized to 0 dBs, and then as the angle moves away from 0 degrees, you can see the energy level drop dramatically. So it's important that when we deploy a microwave link, perhaps at the regulated 80 gigahertz band, to relate this to small cell emerging technologies, perhaps at 40 gigahertz, perhaps at 6 gigahertz and 11 gigahertz, it's crucial that the off-axis radiation stays under the line, or at least at the level that the link or the network was planned to. The right-hand graph is an actual measured set of results. So we were very disappointed to have discovered this antenna that was being sold on the market, stated as compliant, and further benchmarking studies has led us to understand and recognize that antennas are declining with time. So sadly, their characteristics, their off-axis characteristics are changing. So the symbols there in Europe relate to the CE mark. In Europe, it's a legal obligation for the radio supplier to meet these off-axis characteristics. In Europe, an antenna with these characteristics would be actually breaching the law. Interference, though, is a global issue. Laws there or not, this problem is still relevant. Next slide, please. So my negative theme will become more positive in a moment, I assure you. However, just one important aspect to consider as well. The interconnection, in fact, the impedance characteristic of the interconnection between the third-party add-ons, so things like couplers that are attached to the back of the antennas and the interconnect from the radios, leakage, poorly engineered and ill-conceived joints that are not well understood will radiate energy. So the graph there shows a blue line, which is how the antenna and a well-engineered joint at the back of the antenna would perform. The red line is purely to do with the leakage from the add-on of a third-party coupler in this case. So be cautious about the devices that you connect to the back of the point-to-point antennas. Next slide, please. So we have, as a company and as an industry, we have some very exciting emerging technologies. I decided to reference 4. In fact, CommScope as an organization, we have 6 emerging technologies, 3 of which we feel are really quite disruptive. I'm only showing one of the disruptive technologies pictured there on the left, called Sentinel. I'll talk to the 3 images towards the center and right-hand side of these slides. The environmental conditions, we're all aware of the worsening effects of the environment. Wind speeds globally are increasing, the effects of tornadoes and typhoons and so on. So to respond to that problem, we launched a set of very strong, very robust products that will take extreme conditions. So that's a fact, that's a simple issue to explain. E-band antennas, this is the emergence of that spectrum for potentially very high capacity, reasonably short licensed links. And on the right-hand side, if you remember, I mentioned leakage from the joint of the antenna to the equipment. Technology is available, certainly from CommScope, and I would hope from elsewhere, where the joint and the impedance characteristics, the match of these devices is engineered properly, such that those problems do not occur. So that's a product offering available from CommScope on the right-hand side. On the left-hand side, like I said, there are 3 disruptive technologies available from CommScope, but I'm going to focus now on Sentinel. So next slide, please. So this is slide 11. Sentinel is different from microwave antennas that have been deployed in the industry to date. It continues to comply with and meet and in fact exceed the existing standards like ETSI Class 3, like the FCC specifications and the other ones listed there. However, Sentinel has dramatic improvements in off-axis radiation, very generally speaking 13 to 15 dBs higher in discrimination of interferers coming into the antenna. But the very core of this product is that its price point is not economically prohibitive. So a small incremental cost in purchase price of the antenna would lead to some benefits that I'm going to discuss on slide 12, please. Next slide. So again, to reference the graph that we showed before, the red line is the freely available high performance or Class 3 off-axis specification. The blue line is the Class 4 specification. So as you can see, the improvements with angle are pretty dramatic, but they do vary a little over the full 360 degrees. Our launch plan for this product is actually to provide 1, 2, 3, and 6 and 8 foot antennas at this diameter, and I'll make the bold claim that we're very happy to defend offline, that potentially in an interference in an electrically cluttered environment, the potential savings, spectrum savings, can be as much as 40%. But the most compelling point about Sentinel is that it allows you to use smaller antennas on your towers, again in a electrically congested environment. Next slide, please. So I'm going to discuss consider a tower. This is purely conceptual to help you understand the point. Consider a tower with many, many links, radio links, connected to the tower. So radially around the tower, let's say we are aspiring to have 10 links coming into that tower. Next. So I've shown on this graph the Class 4 specification, the Class 3 in blue, and the Class 2, which should not be used. Generally for spectrum preservation and future-proofing our networks, we shouldn't use Class 2. But for interest's sake, I gave you the Class 2 off-axis specification as well. Next. The table that will emerge on the right gives you a sense of the power of Class 4 antennas, the Sentinel antenna. If you consider Class 2 and a co-channel or a required C over I, carrier to interferer requirement of 40 dBs, and you move across the 40 dB line there, you'll find that the Class 2 antenna intersects at about 60 degrees, the Class 3 at about 45, 46 degrees, and finally the Class 4 at about 15 or 16 degrees. So if I divide 360 degrees by any of those numbers, with Class 2, 360 divided by 60 is 6. So I can have 6 radio links if the C over I requirement is 40 dBi or better. But if I use Class 4, I can have as many as 22 radio links on that tower. So again, this gives you a sense of the C over I benefit that you might get from a tower in that conceptual configuration. I don't mean to claim that this is a real scenario, but it gives you a sense of the immunity. Next slide, please. Next. In the case of this conceptual situation, I've got 2 radio links, and one of them is a problem. Next. All I can do today, if I have an interference threat coming from an adjacent link, in order to increase my C over I, my carrier to interferer, all I can do is increase the size of my antenna and increase and get basically an increase in gain from the new antenna. So if I go from a 2-foot to a 4-foot antenna, I may give a C over I improvement of 8 dB. I may achieve around about 8 dBs for this scenario. However, if I replace my 2-foot antenna, my 2-foot Class 3 antenna with a 2-foot Class 4 antenna, on the right-hand side, I can show you for the same antenna size, I get a C over I improvement of 14 dBs. So this becomes very powerful. It means that I can use the same size antenna and resolve an interference problem if I use the Sentinel antenna. Again, a conceptual illustration. Next slide, please. This is my favorite slide. We used our analysis tool called IQ-Link to analyze a situation where again, a fictitious model, we needed a C over I performance of 23 dBs. We used two 2-foot class 3 antennas on the link, and we found that we could only achieve a C over I performance of 19 dBs. So we looked at the conventional remedy to that problem and took two 4-foot class 3 antennas and found that yes, we could achieve 23.02 dBs as our C over I performance. So good, our link now will work. However, as an experiment, we took two Sentinel 2-foot class 4 antennas. In this case, the C over I benefit is shown to be around about 17 dBs higher than required, so well over-engineered. So immediately you can see that instead of using two 4-foot antennas, I can use two 2-foot antennas, or continue to use two 2-foot antennas, which was my objective originally. And if you look at the bullet points down on the chart there, you see that there is a reference to dollars. The typical leasing costs I chose $100 per foot per month per antenna. So if I use two 2-foots instead of two 4-foots, I save 4 foot per month on the radio link. That's $400 per saving in ongoing ownership costs for that radio link that I was able to remedy using a Sentinel antenna. I can tell you the 4-foot, the $400, the payback, I'm going to say is roughly around 1 to 2 months in price delta. Next slide, please. So the resounding conclusion is that Sentinel is a cost saver, particularly on a TCO basis, total cost of ownership. Next. So I'm going to hand over to Tom Anderson. He's our Director of Broadband Product Line. Thanks everyone for listening.
Actually, John, you're handed back over to Philip. I'll hand back over to Tom. So thanks you, John, for the overview of the microwave antenna technology. You know, I've been in the industry for quite some years, and I think our customers, our user operators, expect to have a really good return on investment. And certainly the investment in radios and the investment on high quality, highly reliable, and high performance antennas like our new Class 4 antenna, the Sentinel, is a great investment. But that investment value can be lost quite easily. So if we just go to the next slide, please. The performance really doesn't just stop at the antenna. There are other considerations as well. Next slide, please. Slide 18, please. There you go. Thank you. So the key area where the investment value can be lost, we've invested in a high-quality radio. We've invested in a high-quality antenna. But if the installation systems that are used in the implementation of that technology are substandard or not well thought through, then that entire investment value can be lost. As all of you know, the most expensive part of owning this type of a system is the cost of installation. So that needs to be done right the first time. And a poor installation system can easily allow an antenna to move. That can affect the path loss. The antenna itself can be damaged very easily. Waveguide, flex sections can be damaged. The tower itself, if the microwave antenna, which can be quite heavy, is not installed correctly, The tower itself can be damaged, and that can cost many, many dollars. And ultimately, a person on the ground can be put into danger. I mean, these systems have to be designed and installed in a way that protect the installer themselves as well as people who may come within physical proximity of the site. So next slide, please. So from our perspective, we think it's critical that the microwave backhaul system be seen as a complete system, a comprehensive system that includes the antenna, the feeder, the cables that connect the radio to the antenna, the coverings, and ultimately the installation systems that go with it. That brings a complete peace of mind that the entire system is thought through comprehensively, using well-engineered structural support to increase stability, and ultimately we believe that provides the best overall investment to make sure that the investment in the radio technology and the antenna technology is fully realized. So with that, we'll change the topic from microwave backhaul links and talk about the fiber-to-cell initiatives that are coming out from CommScope. And with that, I'll turn it over to Tom Anderson from our broadband division to talk about fiber to the cell. Next slide, please.
Thanks, Philip. This is Tom Anderson. And if we can go directly on to the next slide, we'll get started talking about fiber to the cell. So as we saw earlier, about half of mobile backhaul is being addressed by microwave systems, and about half is wireline systems. So we thought it'd be a good thing to talk today about a couple alternatives in wireline and what's possible there. I mean, wireline has traditionally, for mobile backhaul, has traditionally been T1, E1 lines. Those turn out to be expensive, they don't scale very well, and they get really expensive really fast. So you really need a different kind of network as we go into next generation kind of backhaul technologies. And you need a system that can be scalable, that's affordable at the hundreds of megabits kind of rates, and will deliver the kind of quality of service that you really need for those faster rates and the kind of expectations customers have from their mobile networks today. There are a couple alternatives to do that. One is to build a dedicated mobile backhaul network. That's extremely effective, and you can get all kinds of quality of service, can dial in any data rates that you could possibly want doing that, but it is expensive, and it gives you another network to manage on top of the other networks you have in your system already. So another alternative is to leverage an existing access network technology. That'll let you increase your return on investment from that technology. It does give you economies of scale, and it begins to get you some network convergence so that you're using one network for all the transmission that you have going on in your system. XPON, and by XPON we mean EPON, GPON, Gigabit Ethernet PON, GEPON, or even 10 Gigabit Ethernet GPON, are all technologies that are widely used today, but they've been regarded as a residential technology. And so the real question is, can PON perform in a mobile backhaul network? And through the next few slides, we'll see if we can answer that question. So next slide, please. So the key requirements in a mobile backhaul network from the XPON system or from the access network system is that it has, first of all, it has to be able to deliver the bandwidth that you need. You have to have quality of service, and in XPON systems that really means you have to be able to address delay and jitter in a way that gives you the kind of end-to-end performance that you need in the network. You need a network that can be converged to deliver both TDM services and packet-based services on a single platform. You need you need endpoint management and monitoring, meaning you have to be able to manage the system to see at any given instant exactly how the system's performing. And the last thing you need is, from an XPON system, is synchronization. And that's to get the timing right so that you're able to deliver those TDM services that you've been able to do in the past with legacy networks and also for future packet-based networks. And next slide, please. PON systems do deliver all those things. So let's take a look at them. So let's look for bandwidth capacity, how much bandwidth you really need. If you're looking at 3G cell sites, probably 30 to 40 megabits is enough. 4G LTE, quantum leap forward in needing 200 to 300 megabits per site. So if you look at what's going on in a typical PON network that's used for residential services, if you assume kind of a worst case, you're probably going to look at a 70% take rate and at 20 megabits per subscriber for internet access, a couple of HDTV IP TV channels, and you're using up about 700, almost 800 megabits of what's on the network already. So if you look at the capacity left in an EPON system or a GPON system, what we did in the chart on the right-hand side is to determine how many cell sites you have capacity for out of any given PON in the XPON system. So for instance, for a GPON system in a 3G network, you could add an additional 46 cell sites. Not that that's a real-world kind of thing that would be going on, but you got capacity to do another 46 3G cell sites on a GPON network. Same, and if you're looking at 4G LTE kind of bandwidth, you can add another 6 sites in any given 20-kilometer run of fiber. So I think what this says in total is that yes, there is capacity there, and it can certainly be used for mobile backhaul kind of applications. Next slide, please. So if you got the bandwidth, can you deliver the quality of service that you need? And you have to be, in a PON system, you have to be concerned about both the downstream and the upstream directions. In the downstream, there's really not a lot of concern for delay and jitter. So PON systems really act as a distributed layer 2 switch, so there is a bit of delay added. But in the downstream direction, everything's broadcast, so there's no real time delay and jitter kind of problems induced by the system itself. Next slide, please. The upstream direction is a bit different because in the upstream you're operating in a multi-point-to-point kind of mode, so the packets coming upstream have to be sequenced. And when they get sequenced, you introduce some buffering and some delay and some jitter into to what's going on. However, that's not enough to really cause concerns in a mobile backhaul network. And if we can go to the next slide, I've got some numbers there that'll should indicate that that is indeed the case. So if you look at from RFPs, we've taken a look at what wireless carriers are looking for in requirements in terms of delay and jitter, and if you consider, it's hard to come up with a hard number here for what the EPON or GPON system itself should do in terms of delay and jitter. And the reason for that is it's only a part of the end-to-end delay and jitter in the network. So it gets its piece. So MES specs would require something less than 25 milliseconds for delay. Typically, a wireless carrier will ask for something less than 12 milliseconds. And indeed, an XPON system can deliver something on the order of less than 7 milliseconds of delay in either direction. In terms of jitter, I won't read the numbers to you here, but you can see that XPON delivers well less than any requirements for jitter in the system. Also threw in the availability piece here in terms of quality of service. You know, you have to have service up and running all the time, and you can get that with an XPON system given the redundancy that's built into most PON systems from any vendor in the PON world today. Next slide. So if you look at, excuse me, converged packet networks and synchronization and timing, which are the two last requirements we have, I think the proof is in the pudding, if you will. XPON systems are being used by network operators today for mobile backhaul networks. And if you look at timing, delay, jitter, quality of service kind of issues, you're delivering the same kind of services over for residential services that you need for the mobile backhaul network as well, meaning you're delivering TDM and voice over IP for voice services. You're in IPTV, which is extremely time-sensitive kind of payload that's going through the network. And you're delivering on the data side of things, you're delivering residential best effort services as well as extremely high quality data services such as you would need in telemedicine for transferring X-ray images around the network. So XPON systems are delivering the services comparable to what you need in a backhaul network today. And indeed, the systems are complying with the timing requirements and the synchronization requirements that you need out of a mobile backhaul network. So you can get synchronization compliant with RFC 1588. You can do sync-E kind of things for TDM backhaul. You can do bits timing, internal clock timing. You can reference timing to T1, E1 clocking. So the synchronization methodology is there and the compliance is there to deliver the kind of mobile backhaul networks that you need. Next slide, please. And I guess the final point here is that in terms of endpoint management and monitoring, you need what's traditionally been called FCAPS performance. That's fault management, configuration, accounting, performance, and security. And indeed, you can get that from an XPON system. You get, with fault management, real-time alarms and statistics, so you can tell what goes on at any time. You can also get redundancy built into the system, so you get, when there is a fault, you get automatic switching to the redundant part of the network. You can do configuration management. There's plenty of northbound interfaces for accounting, whether you do that through a web-based GUI or SNMP kind of functions. And one of the other things that you can get out of a PON system is security. For data encryption, there's AES 128. You get management access control. You cannot get access to the network other than it being allowed through the OLT management system. So it's an extremely secure network transport as well. Next slide, please. So to kind of sum all that up, EPON, GPON, 10 gig EPON are used in mobile backhaul networks today. It does serve those five factors that are really critical for making a mobile backhaul network work in terms of bandwidth, quality of service. It's a converged network, so you can deliver all your network services over a single system. and it gives you the endpoint management and synchronization you need. So, and it also does a very important thing in terms of return on investment, and that's it lets you use the network that's there today. All you have to do to add mobile backhaul is to add an ONU into an existing PON system, and you get the scalability that you need, and you get it simplified to a converged network. So that's a real quick view of PON as a mobile backhaul transport. And with that, I'm going to that brings the presentation portion of this to a close. I'm going to pass the speakership over back to Jeff and see if we can answer some questions for you. And Jeff, are you there?
Thank you. Yeah, I was on mute. My apologies. Thank you, speakers, for staying on time. We've got about 10 to 12 minutes left. And what I'd like to do is share the results from our initial poll before getting into Q&A. And the first poll was, what is the current state of backhaul in your view? And it was basically equal between folks having challenges today versus over the next 18 months, or the final response was they're 2 years away from having a real critical challenge with backhaul. At this point, what I'd like to do is share a second poll and leave this open for just 30 seconds or so, and ask everyone on the call to give us your views on your most important consideration in backhaul planning today. So we'll leave this open for a few minutes while we open up the session for additional questions that can be submitted online. So please take a few minutes and submit some questions, and we've got plenty of time here to address them for the next 10 minutes. Philip, do you see any surprises in that initial poll, or is that consistent with what you're seeing from your customers as a whole?
I think it's fairly consistent. You know, depending on the maturity of the network and really where different operators are with their implementation of LTE in particular, and the maturity of 3G networks for some, that's fairly typical kind of response that we get. I think everybody sees that the backhaul capacity has to be addressed. Certainly with some, we wish we had done it ahead of time now, and some have some believe they have some time to work through and kind of plan it out a little bit more effectively. So I'd say overall that's pretty consistent with what we hear.
Okay, we're getting good responses to the second quick poll. We've got about 60-some-odd% of the folks have cast their vote. And by the way, people can click on multiple buttons, which is why the numbers add up to more than 100. But I'm going to leave this open for a second more, and then just close the poll and share the results. Okay, last chance, attendees, if you want to vote on this last quick poll. Okay. So it looks like, what are your most important considerations in backhaul planning today? Stability and reliability of the backhaul link is number one, followed by capacity increase gains, followed by lower cost, total cost of ownership, and then cost containment and equipment purchasing. And I'd love CommScope. Philip, any comments there? Is that consistent with what you're seeing with in the market?
Well, what I would say about that is it looks like a lot of people would agree with a comment that I think John Cole would say, which is as you achieve better stability and reliability of the backhaul link, you also get capacity gain. So solving that reliability and stability problem also adds to adding capacity. So those things are very, very much synergistic. So I would say overall that's a really good response to in the poll questions, and really gives us some good feedback as your suppliers to help us really confirm that we're working in the right areas that's needed in the industry.
Okay. Well, let's jump over to, I'm sorry, any other comments on the poll results?
Yeah, this is John Cole. I'm very pleasantly impressed with the response to that poll. So we're constantly struggling with the dilemma of reducing upfront purchase price cost versus C and D on the poll there. And as Philip says, we favor C and D, and by the way, A as well. But the delta is very, very narrow. So this is about investment, and it's about the pressure points in the acquisition of the network, and certainly examination of where those pressure points are, and the behavior of the team from inception through to completion is a very interesting topic, and that's a fascinating result for me to see.
Okay, well, good. Let's jump over to Q&A from the audience. One of the early questions we had was, can you describe the third-party connector noise issue in more detail?
I'm sorry, that's for me, yes. It's a simple issue. The interface between the antenna and usually a coupler, but sometimes a OMT, an ortho mode transducer, has not been considered. So when we use the phrase third-party add-on, it's a fact that the device and the data sheet for the device may be declared as being suitable to fit to X, Y, and Z products. So if I manufacture tires and I declare that they're suitable for your Mercedes, do you believe me? My point here is be very cautious as how you accept that declaration and qualify that declaration. So essentially the coupler, OMT, and antenna, coupler or OMT and antenna, as they're engineered together, there are some strict mechanical, water ingress, and particularly RF radiation issues. So for instance, choke grooves and O-ring grooves, these are engineered features that have to be compatible. And it takes clever engineers to figure out both interfaces to make sure that RF leakage doesn't occur. So if you have two sets of engineers working independently, one on the third-party add-on and one on the antenna, then it's likely they'll get it wrong, or there's a substantial chance. So again, we're asking you to be cautious about how you allow that connection to be presented or deployed in your networks.
Okay, thank you. One of the questions was, are Class 4 antennas in current use today?
Yes, keep in mind we have only just launched this technology, so I can tell you that we have a great deal of excitement. We have a backlog to ship them, and there are some pilot links that are deployed right away. In a sense, this antenna, to simplify it, it can be simply considered to be bulletproof to interference. That's a nice phrase to use where you don't know where your interferers are coming from, or where you have unidentified problems, or where the database in the planning authority is poor. Then the use of Sentinel will immunize your link to interference. And this seems to be, there are either good link engineers who are utilizing its characteristics and optimizing, making very special savings in the overall network cost, and there are other guys who are solving problems in the network and remedying interference threats.
Okay. As we move to small cell backhaul, do you think the backhaul will be primarily fiber or microwave?
Well,
I'll take a cut at that one. I think
yeah,
right now we would have to say the jury is still out. There's pros and cons. There's pros and cons for both technologies, and there's pros and cons both on a technical standpoint and a logistics standpoint, and just physical, how do you implement standpoint. So I think as small cells continue to evolve, we'll see. I think we'll continue to see a mix of both the technologies. I think on the air interface side, there's some technological leaps forward that probably will occur that will enable that to continue to be a very viable method. And I believe on the fiber application, there'll continue to be simplifications that are made, as well as commercial applications that are made that will continue to move that forward. But I'd say today, exactly what the mix is going to be, even roughly, I think the best estimate would be it's probably going to be roughly about what it is today going forward.
Okay. I want to jump back. Somebody, when we talked about Class 4 antennas being available, someone asked if they're available in the U.S. market today, and are they considered FCC Type A? Not sure what that Type A means, but maybe you could respond to that add-on question.
Yeah. So yes and yes are the two answers. By the way, there's a lead time on delivery, so it's a matter of weeks, perhaps 8 to 10 weeks for you to place an order to receive them, and this is just because we have a delay in getting brand new units from Europe where they're being manufactured initially, but we're setting up production in the US as well. So lead time will come down to 1 to 2 weeks with time. And as for the specification category A, yep, we're in good shape as well. By the way, a lot of frequency bands to think about, so you would have to talk to your local sales account person to get real details on the which band is available.
Okay, good. Currently, backhaul links are coordinated in order to avoid interference and to maximize spectrum use. Does this coordination become tougher as data traffic demand rises?
Well, I have a very biased view on this topic. I would, if I were a regulator or an operator, I would default to the tightest specification antenna, particularly in urban environments, to the tightest off-axis radiation characteristics that I can get at an economic level. And I would do that because none of us, so as the traffic demand and the capacity demand increases, it's inevitable that more and more radio links are going to go in. So Philip was talking about, or we were talking about, the trade-off between fiber and radio at millimeter waves for small cell. I'm sorry, at 80 gigs, not 60 gigs, at 80 gigs for small cell. I would put in very tight Class 4 patterns if there isn't a cost penalty. That means then that new links that arrive en masse, if that's relevant, in an urban environment, can be coordinated easily with the existing links that we deployed weeks or months or years ago. So definitely as data demand arrives and more and more links and channels are needed, if we all had thought ahead and future-proofed our networks, one of the things we would have done is put tight radiation patterns into places where there's no spectral interference because of the day when it may well arrive.
Okay. Well, we're at the end of our hour. I'm going to leave a last commentary. Philip, if you don't mind, you can see that we have more questions than we have time to answer. Do you see any other questions that have come in that you want to address before we do a closing wrap-up?
No, I think we need to go ahead and close out for the
Okay.
everyone on the audience. Again, from a CommScope perspective, I certainly would like to thank you guys at RCR for hosting us, and for all the people that did dial in and submit questions. We are very interested in continuing the dialogue. One of the benefits of participating in forums like this is that we have like-minded people that are trying to take on challenges in the industry and come up with creative and innovative ways to move the whole game forward. And again, I'd like to again thank you guys at RCR for hosting this today and letting us participate.
Well, thanks for your time. Thank you all who submitted questions. CommScope will be receiving a list of questions, and we reach out to folks directly with any open questions. We will be making the presentation available within 24 hours. And if you have any other questions, please feel free to reach out to RCR directly. Thank you again for your time. At this point, we're going to close out and end the webinar. Thank you.